All right, so let's shift gears a little bit and let's talk about what we do for an object on a ramp. And this changes things just a little bit. We still have a sort of our common sense uh, things going on here like weight and friction. It's just that they shift into an angled perspective. So kind of let me show you what's happening on a diagram here, and then we'll break down the force of gravity into a couple other forces. So if you think about it, this object is still going to have a force of gravity pulling down on it, or weight, right? And that's going to be equal to mg, all right? And then if the box isn't sliding, or even if it is sliding just a little bit, we should have some force of friction. And then we're going to have the ramp supporting the weight of this object. But remember, force of friction is always parallel to the surface of contact, and our normal force is always perpendicular to our surface of contact. And if you look through this, now I may not have it perfectly drawn to scale here, a little bit off, but those three vector forces, if this is an object that is sitting at rest, should cancel each other out. We've got these two things upwards with that one downwards. Again, it's not perfectly drawn, but you sort of get the idea there that this has an x and a y component, and this has an x and a y component, and the x components would cancel right and left, but the two y components would add up to be enough to balance out the force of the weight. So we could have this object sitting here with a net force of 0 and have it not accelerating. One way to think of this force of gravity, though, is that it's actually broken into two other forces, one this way and one this way, and that breakdown is how we end up figuring out what this normal force and our force of friction are. So if you want to find what the force into the ramp is, that force is going to be equal to mg times the cosine of the angle of your ramp. So therefore, when these two things are in balance, your normal force is equal to that. And then you would have the force going down the ramp. That's going to be mg sine theta, and that's how we can oftentimes figure out our force of friction. So this vector force right here of gravity really gets broken down into these two components to help us figure those out. But the real free body diagram really shows just the gravity and then these two things, okay? So you can pause the video, write this down in your notes. Make sure that you have this because you're going to look back to it several times, all right? So let's go ahead and do a problem with that. So here's going to be my flat surface, and I'm going to put a ramp. And then it says that I have a 40 kilogram box sitting on a ramp at a 35-degree angle. And they want to know what force of friction is necessary to hold it in place. Okay, so let's go ahead and get our forces here. So I'm going to go ahead and show this force of gravity is equal to mg. So that's 40 kilograms times 10. That's going to be 400 newtons. All right, so let's go ahead and break that down into this force and this force. So this one is going to be mg cosine of theta, which is going to be 400 newtons times the cosine of 35 degrees. And I get, let me just double check that here again. Oh, we're good. All right, so that's 320, we'll call it 328 newtons. All right, so this is 328 newtons. Let's go ahead and find the force down the ramp. And to save some space here, I'm just going to do 400 times the sine of 35 degrees. I get 229 newtons. All right, well, this box is motionless, so I know that all my forces are in balance. So then my normal force has to be equal to this force, which is 328 newtons. And my force of friction. So then our force of friction then, because these things are in balance, are going to be equal. So that's going to be 229 newtons. That's the answer to what our force of friction is going to be. So then we're going to call this a bonus question. And at that coefficient of friction,